York. And she is a civil engineering doctor candidate with a focus on water resources and environmental engineering. And she's interning with NOAA Center for Weather and Climate Prediction and KICS, and her mentor is Dr. Tom Smith. And Equisha has completed an internship here previously, and she has continued the research she studied regarding the climate change in Caribbean and the impacts on the surrounding regions. And she is interested in understanding the drivers of Caribbean climate and impacts on water resources to help develop water management strategies to mitigate impact of the climate change on water availability. Okay, let's welcome Equisha.
Hello? Hello? How do you do it? Turn it up? Okay. All right, thank you. I don't want to be too loud. Is it? You guys tell me? I don't know. I can hear myself up here. No. Okay, great. Okay, well, thank you, John, and thank you all. You know, you guys didn't have to skip AGU just to come to my talk, but thank you so much. Okay, so yes, we'll get right into it. So as you see from the title, we're looking into what's going on with precipitation, not just in the Caribbean, but the Caribbean and surrounding region. Yep. No, it's not advancing. Okay. Almost. No, it's just not advancing.
I think we might have to. Was it not focused?
Yeah, that's what it was here. So. Oh, sorry. It wasn't focused. Okay. So yes, the Caribbean and surrounding region. So this is the entire domain that we're actually looking into. And what's going on here is that we have decreasing precipitation trends, although we have warmer sea surface temperature trends. But I will get into that. So first, okay, why this region? I know a lot of people think, and they saw Caribbean, you think about your vacations and things like that. Well, yeah, that's one part of it. But especially lately, we know that we have to deal with hurricane activity. And so, of course, this region is where, you know, hurricanes pass through. They've been very devastating as of lately as well. We have moisture transport and availability. So the trends of moisture being transported through this region can influence the amount of moisture that we'll receive here up in the U.S. And then we have a whole lot of coral reefs here. As some of you may know, some of you probably study, you know that they are also very sensitive to climate changes. And then we're dealing with water resource issues as well. So we have the coast. A lot of people live on the coastline. But then we also have what we call the small island developing states. So you have all these independent places. And, you know, what water you have there is what you have. So they have been experiencing changes in the amount of water that they are receiving as a result of these climate changes, and then that results in impacts to agriculture as well, and then, of course, like I said, tourism. So, believe it or not, this region is actually really understudied compared to a lot of other regions in the world. And from a lot of studies, a lot of literature, you'll see it's because of data. So if you want to do like a climatology, a long-term study, it's harder to get long-term records that are complete. And so we're a remote sensing center at CREST and NOAA CREST, so we look to remote sensing to try and fill in these gaps as best as we can. And then, like I said, the extreme events that we're interested in. We have the moisture transport to the U.S., and then the sensitive ecosystems. So understanding how we designate seasons here, so there's no summer, winter, fall, right? We go there in the winter because it's warm, right? So they care about rain. So their seasons are designated or characterized by their rainfall patterns. So what's interesting about this region is that it has two rainy seasons. Instead of a long, continuous dry period followed by a continuous rainy season, they have two periods, and that's because they experience this midsummer drought. So it's not a drought in the traditional sense that there's no rain. It's just that it's a significant drop in the rain right in the middle of this rainy time. So you have all this rain happening here, starting from April, going through June, and then once you reach July, you get a significant drop. And then it picks back up even more so after this drop, starting around late July and August. Now, it doesn't look like such an extreme decrease here because this is average over the entire region. So it actually shifts as you move from east to west in the Caribbean. So if you're in Puerto Rico, say around June, you would actually see a sharp decrease. And then as you move westward, more towards July, later July, that's when you will start to see this decrease happening. So just keep this in mind. This is very important. We have the dry season, December to March, early rainfall season, April to June, and late rainfall is August to November. And July was left out because of that drop in precipitation that marks the two seasons. So here's the data inventory that was used for the study. So, of course, there was precipitation data. That was from GPCP. A lot of you may be familiar with that. But the thing that really, I guess you could say, set the whole stage for this was the optimum interpolated SST, the NOAA product. And that's because it has a high resolution. It was daily. It covers the region well. And it started from at least the 1980s. So this is why this is a cutoff point for us. So 1982 was the first complete year that they had with this record. So that's where we start, and then we go on from 1982 to the present. So we use GPCP because it covers that same period, and it's also been stated to be appropriate for this type of analysis, especially in this region. And then when we want to look for convection, which you'll see later, you need temperature, relative humidity data, and then ground stations to see if what we're seeing is what we're seeing, right, from the satellite data with the precipitation. So overall, these are the tests that were performed on each of the variables. So it performed a trend test. I'll get more into that just in case people are not sure what the Mann-Kendall test might be referring to. And then principal component analysis. At this stage, it was only used on sea surface temperature and precipitation, and then some modeling just to see if we could explain the precipitation with the SST. So this is where it started. So when I came here previously, we looked into sea surface temperature trends. And from there, we saw that sea surface temperatures in this region are increasing, but they're actually increasing at a slightly faster rate than the global rate. So it's warming, it's getting warmer here, and it's happening faster here than in a lot of other places in the world. So it is happening per season, and as you see, the distribution changes as you move through the seasons. But overall, you have significant warming, especially more so during the late rainfall season, when you have the warmest sea surface temperatures, and then some warming during the dry season. But it wasn't enough to cause convection, so this might actually potentially lead to a drying trend. But we'll see, right? So The interesting thing about the sea surface temperature warming, though, is most of this warming is actually happening during the later half of the period. So it's not like it's been doing this, continuous the whole time. It's just been increasing more so during the past 15, 17 years or so. So that was something interesting to see as well. But now we have this in mind, and sea surface temperatures are shown to have a 5-time-fold increase on precipitation when they're really warm. So it's a sweet spot. It's not like you just have warm sea surface temperature, you have more precipitation. It has to be between 26 degrees Celsius and 29. So that's like the sweet spot where you really would see influence from sea surface temperatures for tropical precipitation. So we do see those temperatures, and we have seen them as far as the increased warming that we're seeing with the sea surface temperature, especially in the late rainfall season. So with this in mind, we're thinking perhaps we'll see maybe some increases in precipitation, right? We have warmer sea surface temperatures. Maybe it'll have that type of effect, but we don't know. So this is just going into what I was referring to with the trend analysis. So I just did a parametric test just to start, but the non-parametric test is more appropriate because precipitation is highly variable, and that's the beauty of the Mann-Kendall test. I'm not sure if you guys are familiar with that, but that's just a non-parametric way to do a regression. And why it's great is because you don't have to worry about assumptions like normal, not normal distribution, missing data, weird space periods in between your data. So it was the most appropriate. So this is just to show that, and it was easier just to show it on JET, but this is just to show that the station data that we could gather matches with the satellite data overall. Now you may be wondering, what about these red ones here and the place that's blue? But it literally was not much of an increase. Like the dot turned red because if the value was greater than 0, it registered as an increase. So, but it's a very, very, very small numbers above 0. So the results were pretty close using the GPCP data. So when we look at precipitation annually, so this is averaged over the whole region, so remember, but accumulated per year. So accumulated precipitation per year. And annually we see it's going down. The same thing for the early rainfall season. But for the late rainfall season, we see an increase. This is during the time where you have the warmest sea surface temperatures, and you're reaching that sweet spot that I mentioned, the 26 degree, 29 degree Celsius temperature. So that was like, okay, we thought maybe we see that. But the dry season is actually getting drier, and it has the steepest drying trend overall. So that was actually very interesting. Wasn't expecting to see that, and now we're trying to understand why. But the dry season was the only season that had a statistically significant trend. So it is drying in the Caribbean overall, but it's drying significantly during the dry season. So this is what it looks like spatially. So this is the slope per point for precipitation. And then the hatched lines are just indicating those trends that were determined to be statistically significant. And for the most part, most of the drying trends were picked up to be the significant trends. So the other thing to note actually is that the southern half of this region actually doesn't really experience this decrease, except for this very interesting blue region here that we'll just, we're obviously going to investigate that, but that was very interesting. So now, trying to compare these things. So initially, because we started off with just SSTs and trying to understand if the trends in SSTs for that period have anything to do with the precipitation that we're seeing during the same period. And so PCA analysis was used on this, so that's why this is the results using PCs, principal components. And basically, this is just saying that annually, you have a significant, statistically significant trend here, here, and here, meaning that the first three principal components of sea surface temperature actually can explain annual precipitation. So they were really closely related. But then you see it's a little more tricky, I guess you could say, when it comes per season. So that's why it's important to see what is driving precipitation generally, but it does vary per season. So the same thing that you have happening in the early rainfall season is not necessarily the same driver that you're going to have during the late rainfall season. So we know annually SSTs do follow the trend of precipitation fairly well just on its own, but we have these other factors that we have to consider. And that's when we come to the convection analysis. So I know some of you may be familiar with a lot of the traditional indices out there. And so when I started this, I wasn't really sure, so I started there. I looked at the traditional ones that you use, usually like K and CAPE and all these things. But I came across this index, the GDI. And as you see, it was developed right across the street by Jose Galvez and Michael Davison. So what's great about this is that this convection index was tailored to model convection in that region, in the Caribbean region. So as you see, it's for the prediction, because they worked at the Weather Prediction Center, but it was for the prediction of tropical convection, but particularly in the Caribbean. So these other traditional indices didn't really capture convection as well as they would like. So that's why they worked to develop this. And so this is just a summary. It does low and mid-troposphere conditions, and you consider these 4 levels, and I'll just go into that. So this is what the true image looks like. This is like April, like August. This is a day in August 2013. And so normally, like I said, we would look at the other indices, and as you see, it doesn't really, they don't really capture this event that well. So you have this shifted here, exaggerated, hot spot here. So K, which actually does a little bit better, and is actually where I was going to start. It does a little bit better, but like I said, it's not the best for this area. So when we have the GDI, and you see the GDI result here, that the Galvez-Davison index, it actually models this pretty well. So that's why we look to using this to explain or try to look at trends in convection over time. So what matters for convection in the Caribbean? So the take-home message here is that we have to also consider cloud depth, because as you see, just a small change in the depth can result in different amounts of precipitation. So the K index doesn't really capture that all that well. And that's something that's a very important modulator for the Caribbean. So this is just summarizing what modulates it. And it's basically availability of heat and moisture. This is the potential temperature. Cool and warm mid-level, so that's why we're dealing with the 500 hectopascals. And then subsidence inversion. And then this is why the different levels were chosen that they decided to use for the GDI. And so you see, like I said, the 500 level is for the moisture and stability. You have 700, and then to 850 to influence of the trade wind inversions, and then you have the near surface heat and moisture content. So they developed different parts, like factors, to consider all three of those things. And this is just summarizing what each of the sub-indices represents. So you have the CBI for the buoyancy, moisture available. Then you have the mid-level warming index, and then the inversion index, which deals with stability and drying. So this is how you interpret the values that you get from the index. So basically, for the purposes of what we'll be looking at, just if it's decreasing and becoming more negative, it's not favorable conditions for precipitation. If it's increasing, then we'll have more favorable conditions for convection and convective processes for precipitation. So just keep that in mind. And this is just an example to see what it looks like, what a validation they were doing here. So you can see the outlines here and how it's matching up. So now, for this, I use NSEP data, like I mentioned before, but I did want to point out, because this is probably very important. So I mentioned that they use 950 hectopascals. Now, that data wasn't actually readily available. So they did say, and they, I mean the developers of the GDI, Jose and Mike, they said that it is okay actually to use 925 in the meantime. If you are able to get 950, then go ahead and do that. And then the relative humidity was just so that you could calculate mixing ratios. So you just need potential temperature and mixing ratios for this convective index at those 4 levels. So this is just to show what it looks like using the data that we had available, just to validate or confirm if it can capture the overall general convective process here. And generally it does. So it's a coarser resolution, yes, but we did want to see if we could use this to see long-term trends in convection changes. So it actually did okay. So now, the interesting thing about this is that this is one of the first times we were actually able to capture the bimodal pattern here with a convective index. So as you see, this is the precipitation. Remember, it has that midsummer drought. And then you have the convection here. And it's also showing this tip here. Now, it's also interesting because the peaks are reversed. But that's why it's important that we look at the individual parts of the index. So this is a GDI. And then remember, I said the column buoyancy index, so moisture. Then we have the mid-trophic, so many things to remember, sorry. The mid-level warming index, and then the inversion index here. And then we'll put them all together. And then there's a lot of lines on one plot. But no, this is just to see individually, like, how to compare them. So remember, the column buoyancy index, we're just thinking about moisture available. So remember, the dark line here is GDI. And then we have this CBI here, which shows during that late rainfall season that you have more moisture available. So this is actually suggesting that this is more of the primary driver for that season, is the moisture availability versus the early rainfall time. And then you have the mid-level warming, and then that's the red line here. And you see as we go down and get later into the season, it actually decreases. And then it increases as we're in the dry season. So I have my notes here too. So it says that the drying trend seems to be dominated by the strengthening of inversion effects during that time. And then we look at the inversion index. And then as you see here, that's the squares, orangey colored line. And that has to do with stability. So overall, I'm trying to make sense of this whole chart. So for the early rainfall season, we have a weaker inversion overall, and the effects of cold troughs gradually decrease as we go into June. And then for the late rainfall season, this is almost the purely deep tropics convection season. So convection is we can hypothesize from this, is the main driver, at least for the late rainfall season. Because remember, we're trying to identify what is modulating per season because it varies. So this is the mean per season for the GDI. And it's just showing that overall the dry season has the lowest values. So this is what we expected. And then as you see, it changes, it flows as we move from that early rainfall season to the late into the dry. But there are the issues, the trends. So we want to know, is it decreasing or increasing, right? So we have decreasing trends annually for convection, but this image here on the right is just isolating those values that are statistically significant. So for the most part, you can see it has to do with the drying, but it captures more for the extreme values, the significance. And then this is what the trends for GDI look like per season. So the interesting thing here is that, okay, we have this decrease here, and then we have increasing convection conditions during the late rainfall season. During that time when we expected, when we had the warmer sea surface temperatures. So it actually is going along with what we've been seeing so far. And then the dry season is showing decreases in convection conditions. So we know that that's not really modulating the precipitation there, but it may be contributing to that drying trend that we're seeing. And then this is what they look like per season for the trends that were statistically significant. And as you see, for the late rainfall season, has more to do with increasing potential condition for precipitation. And then for the dry season, it was for pixels that were showing a decreasing favorable conditions for precipitation. And then when we correlate the two, the GDI and precipitation, this is just showing that they have higher correlations here, mostly throughout here, a lot through the dry season and the late rainfall season. But for the early rainfall season, convection is only part of the story, really. So we have other things going on in here. Like I said, it has to do with the mid-level warming and inversion and the troughs for this region, potentially. So that's probably why we don't see as much of a correlation here that we do for the other two seasons, the late rainfall and the dry. So in summary, we were able to use a lot of available satellite data to try and do a climatology, climate analysis of this region. They seem to do okay for what we have. Of course, things get better, but they kind of just recently have improved, so we still need longer time records. But in the meantime, we do have data, satellite data available that actually does a decent job of trying to give us an idea, a general idea of what's going on in the region. And then, as you saw, the SSTs are increasing per season and annually, and at a slightly faster rate than the global rate. And that precipitation is showing a decreasing trend overall, and that the dry season is the steepest drying trend. And then this is just to show that annually SSTs can explain the precipitation annually, but then per season there are different modulators, and the GDI actually gives us look into what those different processes are that may be dominating precipitation behavior individually for each season, and overcoming maybe what would have been the effect of warmer sea surface temperatures. So next, I'm going to try to get this out, published in a short letter. Of course, I'm going to look into teleconnections. I know that was going to come up with a question for sure. So I was going to say, what about ENSO and MJO, MAO, NAO, maybe some other O that I might have left over, but I know it's coming. But we're definitely going to look into that. And then I'm going to look into the vertical wind trends, the Caribbean low-level jet, and then try to model these all together to best make predictions about precipitation behavior based on all these variables, determine which ones are significant, which ones explain it the best collectively. So, thank you. Well, we're AKA Crest. We have a name change. We're Spatial now. So thank you. I know that's going around, a lot of name changes, right? And this is just the acknowledgements for the data. If you guys are interested, especially for the GDI, I highly, highly recommend you guys look into this index if you're looking into tropical analysis. And then, of course, I want to thank all you guys. So let me knock on your doors and ask you questions or say hi to me in the hallway. But no, I really do appreciate being here. You guys are always so welcoming, and I always get so many amazing things done when I come here. So I have to try and be productive now in New York. But thank you so much for your time. Thank you everyone online too. So.
Questions?
So not to put more work for you to do, but have you thought about looking at the shorter time scales, rainfall, to see if there's any changes in number of events or intensity changes? Because you can get on a monthly scale, you can see trends, but is it coming from a few really big events, any changes like that, which are, like we're seeing in other parts of the country where we get more extreme events,
No, that's a really good question, actually. I'm glad you brought that up. So that's something actually I should have mentioned. So there are studies out there that are saying, yes, what is actually happening is that, so they're getting less rainfall overall, or less accumulated, but unfortunately it's becoming the situation where they have less rain events, but when they get them, they're really intense. So you can't, it's causing flooding and things like that, so it's actually not very useful when you have a whole lot of extreme rain events. You'd rather just have some rain more often than to have just a whole bunch of water dumped on you at one time, every once in a while. So that's actually the case of what's going on there. And I know that Robert Adler is actually looking into stuff like that. He's seen the same thing. So that was a question.
I talked already. Now I suppose that you produce all these figures by MATLAB.
Yes.
Have you ever tried to use R or Python? You said you learned a bit to use R or Python to produce any of these figures?
I would love to do that. I would love to produce these figures in anything but MATLAB because MATLAB is just, it's so great for some things, especially when I do with all these matrices and things. It's great for that, but I don't understand why the plotting is the way it is right now. So I would like to. I just really haven't mastered it in R. So if I could figure out how to just make these figures in R, that would be great because I do like the way they look. I've seen, figures generated in R, so I would go there since I have some familiarity with R. I don't really have any experience with Python. My talk was that
Okay,
That
Nick.
good, huh?
Thanks
It covered
for
everything.
again.
Okay. Well, thank you. Thank you for your time.